Good morning. My name is Sudipta Mondal and I am from Anubal Fusion. Anubal Fusion is a private initiative that supports high-intensity laser plasma research with a long-term goal for producing clean, safe, and limitless energy via laser-based laser-driven fusion. So ever since this historic ignition breakthrough by the National Ignition Facility has been reported in the late 2022, nearly in every attempt, the energy gain is increasing by them. They are breaking their old world record nearly in every attempt. And this is reflected by the publication in this chart I have plotted, the approximate number of publication in this area in every year, and there is a jump around that period. And last few years, this is mainly one of the reason for increase now in the number is the commercial funding is coming to this area. And as a result, there are several fusion companies founded, and this world map shows what are the notable fusion companies around the globe, and Anubal Fusion is one of them, an Indian initiative, and located in Hyderabad. And our mission is, of course, our main goal is to produce the laser-driven fusion energy, but this is a long-term goal. It cannot be achieved in a very short term. So to achieve this long-term, we have several intermediate short-term goals that need to be achieved. It starts from laser development to kilohertz repetition rate or high repetition rate laser plasma experiments to targetry to then secondary source generation and their application. This can generate intermediate revenue to drive the fusion research. And finally, a prototype should be designed. And because of this, for that R&D, so lots of R&D is involved in this project. So for that, Anubal Fusion and TIFR joined hand and came to a research agreement, 5-year-long research agreement in the initial period. And these are the people who are involved from TIFR side. The founders, these two gentlemen are the founders of the company who is giving us the chance. And right now, nearly 9 employees are working from Anubal side in Hyderabad, TIFR Hyderabad campus. So to produce any commercial prototype device, we need to solve few challenges. One is the lasers. We need high repetition rate, high power lasers. Nearly all high power laser experiments are short limited. It's very low repetition rate or single shot experiments. But a commercial device should be nearly continuous. So we have to spend some time for the laser development. This laser development will start very soon. And second is the optics development. In high repetition rate, the optical life cycle of the optical component will reduce dramatically. And there is a proposal for developing the plasma optics. Most of my talk today is concentrated on the plasma optics development or some simulations, PIC simulations around this plasma optics development. And the third important thing is the targetry. This is one of the solid target that is we tried to use in my previous job for high repetition rate laser experiment. The solid target is the circular disc behind this tower, and this works for 40 to 45 minutes. After that, we have to change it. And since this is a large diameter target, it gets unstable when it rotates. So this tower in front of it is actually optical stabilizer. It gives a real-time feedback to the motor actuators behind it to stabilize. So we came up with another solution. It's a free-flowing liquid sheet target, and this is the targetry. The target is only in this area. Rest is the 5+1 axis motorized control. And you can see the liquid sheet here, and laser has to be focused in the middle of where the target is really smooth and something. This can run for days and probably weeks. So in this plot, I plotted the laser power development, and current development is this high power laser around this year. Recent addition is the LINP 10 petawatt laser. And this is one of the focusing mirror shown here from 2 petawatt laser, which is around 40 centimeter in dimension. For 4 petawatt and 10 petawatt, it is even bigger. And since it's a focusing optics, it sees the liquid target that I explained just in the previous slide. So it shows all the liquid debris from the target tree. It is very close and it gets damaged, and it's very expensive one. So therefore, the community already recognized that this is a problem. If we have to go from higher and higher laser power, which is proposed here by China, we need to go, at least for the final few optics, should be something different. Conventional solid-state optics will be very expensive to replace. And in this recent publication also discusses these issues. And the good thing is that nearly all parameters a laser pulse can be described, plasma can change it. So we can go to a plasma-based optics. And our plan, at least in the initial few attempts, we want to use a free-flowing liquid sheet in vacuum to demonstrate the plasma-based optics, or because we don't want to change in every hour. So that's why, and we are trying to attempt in high repetition rate, or a low gas phase low density targets for plasma mirror medium. So motivated by the recent publication and the demand of the project, we tried few cases by particle in cell simulation. This one is attempted by Lakshman. He has a poster behind you. What he attempted is he took a low density medium and imprinted a Fresnel's zone plate-like structure in the medium by another two lasers, interfering 2 lasers on them, like what is explained in this paper. But he took it idea to even further. He mixed this with a refractive lens and Fresnel's zone plate together in a third and made a achromat-like focusing of plasma optics. And since Fresnel's zone plate cannot focuses different wavelengths at different places, so achromat will focus, but yeah, we have some losses due to the diffraction, but now he is trying to reduce the diffraction and improve this efficiency, focusing efficiency further. A grating is an important piece of optics that also can be converted to plasma optics, and Imran is working on this topic. He took 2 different laser pulses and focused on a plasma slab in a solid overdense plasma, and plasma gets modified, structure gets modified and make a grating-like structure. And he showed that there is a parameter window where the grating survives, and it can be used as a sinusoidal grating, plasma-based sinusoidal reflecting grating. And in this parameter, he shows the lifetime of the grating. And he also showed a parameter where the grating, these peaks of the grating gets sharpened and becomes a nanotip-like structure, which is the nanostructures we are using in experiments for a long time. And these are dynamically controlled and optically controlled structures. You can change the spacing, you can change the length, and he has used it as a target and showed that protons energy can be enhanced drastically. This is a very preliminary result. We still need to understand a lot before we go for publication. But he has a poster. If you are interested, you can see. Another piece of optics is the deformable mirror. Deformable mirror in high power lasers are generally used to optimize the wave front, reduce the aberrations in the beam, to reduce the spot size and on the target, because it's all about the intensity. We need to focus the laser as small as possible. And you can see this is a picture of the deformable mirror. And this deformable mirror is for 800 nanometer, which is transparent. The membrane is transparent for visible light. You can see the actuators behind it. This is the back side of the deformable mirror. Shivam took this idea that he took a underdense medium, and the density he tuned accordingly, and he sent an aberrated laser pulse through this, and he has successfully shown that the aberration can be corrected. He took at least 4 cases, 4 different aberrations orders in this. These are the different, so tilt, focus, And so I don't remember the last two, sorry, here. So 4 different cases, and any linear combination of them can be corrected by changing the density, just by changing the density in the underdense medium. When it passes through, it corrected, and he has corrected. He has corrected nearly 1 wavelength, which is close to, say, 0.5 micrometer peak to valley. This is a typical wavefront in a petawatt laser, to a nanometer, few nanometer, which is the normal wavefront deformable mirror in the wavefront loop can correct in a adaptive optics loop in a petawatt laser system currently used in the experiment. And Moni is responsible to demonstrate all 3 cases, or few of them at least, in an experimental wise. Since we don't have the experimental facility ready yet, he is trying to shape liquid surface, and his idea to finally take it to the free-flowing liquid sheet target and modify them with the radiation pressure, and then use a second pulse to generate a plasma optics. And that can survive with a very high damage threshold and can be used in the experiment. He has successfully shown that the grating can be generated not only by the radiation pressure, but also something like refractive index modification similar to the thermal lensing effect. And this slide shows different kind of secondary sources that laser plasma interaction produces. So TIFR has a long history for a long time. Even during my PhD, I also worked on these similar topics. It produced different kinds of particles, high energetic particles, and electromagnetic radiations. So we want to take this to the next level, use some of them to use for applications and make a commercial device. And in the first attempt, we use a 10 kilohertz laser, which is currently installed in TIFR Hyderabad, and focused on a liquid cylinder. Since our target is liquid leaf is not ready yet, so we used a liquid cylinder, which is easy to produce, to generate electrons, high energetic electrons, and that converted to the Bremsstrahlung X-rays. And then we put servo motors between the detector and the X-ray source, very close to the X-ray source, and rotated these servo motors, took the projection image in every rotation, and with some computer algorithm, we converted this projection image to the slice, tomographic slice, and produce a tomographic, reconstructed tomographically. And this video actually shows how it is produced. And there is 2 rings here. You can see these are actually damage in the things, damage in the CCD camera, and this can already recorded sub-micron structure. So we can create, sub-millimeter structure. So we can say that we have already successfully demonstrated microtomographic based on laser-based X-rays. So this is our first experiments that we have attempted. And on the fusion goal, since we are very early to say anything, even the technical design is not ready yet, but first experiments has been decided that we will use a kilohertz laser on a liquid leaf target to produce high energetic proton beams, and that proton beams will interact with the boron target to demonstrate the proton-boron fusion at kilohertz repetition rate. We don't need very high energetic proton. This curve shows what are the proton energy we'll need. It's around 600 keV, less than 1 MeV, which can easily be produced with 10 millijoule femtosecond laser. But this will not produce any gain positive. For gain positive, we need some kind of target confinement or compression, but this is too early for us to say anything before we have any technical design ready. And thank you for your attention. And if you think that your research is important for us, please write to us. We are open for collaboration.
Okay, thank you, Sudipta, for a nice talk, and we have plenty of time for question and answers. Okay, so Ganesh.
Thank you for. I don't work in this area. Just some curiosity questions. So you said in the beginning that when you set in the laser in that liquid target and throws a lot of debris, right? You said it gets dirty or something like that in the the beginning, right? So can you explain the process? I mean, what is the plasma physics of it? So you have a liquid target and you shine laser through it?
Yes.
And then what happens after? You produce a plasma inside the liquid?
On the surface of the liquid.
On the surface of the liquid.
Yes.
It's not isn't it more difficult? You can just not have a solid target?
Yes, but since, so that was, we attempted here. So this is what we used in my previous job in a beam line. And this laser was a kilohertz laser.
Okay.
So idea was to shoot the laser on the solid surface.
Okay.
And you generate XUV radiation, high order harmonics.
Correct.
And use that harmonics for other secondary experiments.
Okay.
So that harmonics should be given to the users as a, so that has to be continuous, repeatable, and reliable manner. But since the experiments are done at kilohertz, with 20 centimeter diameter, it survives only for 40 minutes.
Okay.
So after 40 minutes, you have to break the vacuum, install it again,
okay,
and start the vacuum. So the whole, after 40 minutes, we lose something like 2 hours.
And why liquid? How does it solve?
Sorry?
If you convert this into a liquid target, how does this problem get solved?
Because the liquid can free flow. You can see, I didn't explain, sorry for that. So this shows the 2 liquid microjets collide here. I'll use this, it's more precise. 2 liquid microjets collide here, and it makes a liquid leaf kind of things. And this one is a catcher, which takes out the liquid immediately from the vacuum outside and circulate back to the system. In that way, it can run for days, weeks, 10 hours, 15 hours, no problem.
Okay.
So we have already demonstrated for 5-6 hours.
And then what happens now? When you shine the laser on whatever that thing, that produces a plasma and
yes, and all it's similar to the solid surface. So all the solid surface plasma-based experiments, it's possible. Only one problem though that we have to solve. It's a vacuum. Liquid in vacuum is a nightmare.
Yes.
Yes. So, but we have solved and we have achieved 10 to the power -4. So that should be okay for most of our experiments. 10 to the power -4 millibar.
And the protons or whatever that comes out of this will eventually be used with a boron target.
Yes. So this liquid is a roughly 500 nanometer to 1 micron thickness, which you can consider as a foil. So target normal sheath acceleration can be done here, and people have already demonstrated that it can be done.
Okay, thank you.
Okay, Santanu.
Hi, very nice talk. So you're talking about the kilohertz applications.
Yes.
And so you ultimate goal is to have a fusion with this.
If not kilohertz, at least 100 hertz.
100 hertz.
Yes.
Okay, so I see that you have mentioned very important challenging things like deformable mirrors and other things.
Yes.
So like that, the dimensions, how do you create those plasma? By first pulse with a laser and then you can do, I don't understand that part.
So it is a very good question, but it's probably too early for us to say anything, how to, we will finally produce this plasma. So these are like academic exercise with particle in cell simulation. We have demonstrated that it is possible. So to generate this plasma, one way simply, we can use laser itself to generate a plasma. We can use another laser with a SLM, which we can change the intensity or control the intensity over the space and send it to the laser, and plasma density can be controlled accordingly. Where there is a laser, there will be ionization, and it will produce a plasma. If there is no laser, it will be zero density, electron density.
And you have to maintain the density gradients, like
yes.
at a very sharp gradient in order to have a
We
grating.
don't need sharp gradient.
Because your grating,
yes.
that ultimately you have to actually shape your tune your plasma density.
Yes.
And then you have to sustain those density,
Yes, we can use the laser which we want to modify. That laser intensity has to be less than the power that the plasma does not change much. So Shibam has done some
Yes.
intensity
Okay,
scaling.
thank you. I'll visit his poster.
Okay, any more question from students? Oh, okay.
So I have more of a programmatic question. So it looks like the final goal of creating fusion energy is somewhat open-ended.
Yes.
So I'm just wondering, in this ecosystem of funding, when you have a very open-ended question and you're working as an industry startup, who's willing to put their bet on this? Is it primarily government funded, or are you still getting angel investors who can, in principle, who are willing to put in funding for open-ended, almost like a research startup?
This is a very difficult question for me because I don't handle the financials, but I can tell you some. Right now, as far as I know, currently all the fundings come from private funding agencies, and all the technical know-how and scientific know-how we are getting from TI for Hyderabad.